How can you solve 120 nodes big traveling salesman problem within just a few seconds? With naive formulation of traveling salesman problem, you won't get much further than 20, maybe 30 nodes, and even that will take forever to solve. So you have to be much more clever with your formulation and also more picky with choosing the solver you're going to use. In my previous video, linked in the description, I talk about using lazy constraints for subtour elimination, and I encourage you to watch that. In this video, I introduce two more tricks to get the performance even higher. Second one being using callbacks instead of iterative approach, like in the previous video. And the third one, using the fastest solver, because it turns out that once you start using callbacks, the difference in performance between the solvers becomes really huge. From my previous video, you might know that what slows down a typical MIP implementation of a traveling salesman problem is the constraints for subtours, and being lazy with them is the number one way you can speed up everything. And the loop for eliminating them in a lazy way is the same for both iterative approach and the one with callbacks, so the one that I will use in this video. In short, start with initial solution without caring about subtours. In case it contains subtours, only then add a constraint that eliminates this particular solution and then start again. This will work the same in callbacks. Code for this solution is available in the description. It is very similar to the previous one, the one from previous video about the iterative one, except for adding constraints in a loop. Now I'm adding them in a callback. Callback is a function that you can register with a solver, and then this function will be called every time we get a solution. You get a chance to filter out certain types of solution that you are not interested in acting upon. In our case, I don't really want to do anything when the solution is not integral, because it's not yet a correct one for a mixed integer programming problem. How does it perform? In front of you, a pretty busy visualization of 120 nodes solved to optimum with this implementation and gurobi. It took just 4.5 seconds to solve it, including some tiny amount of compilation time, unavoidable on first execution. But this is of course just a single execution, so it can vary. How does it work when we execute the benchmark consistently? For the problem of size 50, with iterative implementation, we needed more than 2 seconds for each problem on median. With the callback implementation, it's just 270 milliseconds. This is order of magnitude faster. With such performance, we can go significantly higher. Well, as you saw with the big 120 nodes, we can consistently solve 80 nodes still faster than the iterative implementation could manage for 50 nodes. Alright, so that's gurobi. And that's in fact the third secret to speeding up TSP implementation, choosing the right solver. Because sadly, with GLPK, the results are so much worse. With just 30 nodes, GLPK in callback implementation needs 1 second for each solution. And sadly, for bigger ones, it stops being stable and does not yield optimal solution consistently. To recap, in improving performance of TSP, there are 3 points. First, using lazy constraints for subtour elimination. Second, using callbacks instead of iterative approach. And third, selecting the fastest solver, which in my benchmark so far, it has been very clearly gurobi. Thank you very much for listening.